thermal physics, and we have been discussing connection between entropy and multiplicity of microstates for a thermodynamic state. And we developed these ideas briefly in the previous lecture, and here we are going to apply these ideas to an ideal gas. So, let me recall quickly what we did in the previous lecture. We had that entropy of a system is equal to Kb log of omega, where omega is the multiplicity. And 2, we found that P, probability of finding a small system energy state EI, is equal to this degeneracy e raised to minus EI over KBT. Divided by Z, where Z equals summation I Gi e raised to minus EI over KBT. And now we are going to apply these ideas to calculate entropy of an ideal gas. So, first thing we need to do in this is counting the states. Now, remember that state of a molecule is given by its position Ri and its momentum Pi. So, to count the number of states, we make cells in the phase space. Review this from physics 102. In 1D, therefore, the cell is going to have a size delta x, delta px. And in 3D, cell volume in 6D space is going to be delta x, delta px, delta y, delta py, and delta z, delta pz. And we take the product delta x delta px to be equal to h, Planck's constant. And therefore, this volume of cell in phase space is equal to h cubed. Second, we count number of cells in a given volume of gas at temperature T. So, this number of cells is going to be equal to the volume in space times volume in momentum space divided by h cube. Volume in space is V, and momentum space volume I am going to take to be some constant times P r m s square divided by h cubed, or this is going to be cube. P r m s is the root mean square momentum. Now, P r m s square is equal to two m, the total energy U, divided by m. So, this gives me P r m s cubed equals, or divided by n, 2 m u over n raised to 3 by 2. Oh, by the way, this is the number of cells available to each molecule. So, I should point that out. This is the number of cells available to each molecule. Each molecule can go into the volume V of the entire container, and it occupies the volume P r m s cube times a constant in the momentum space. Since I am going to take log later, so that constant does not really matter. So, therefore, I can write with this, the third step is going to be the number of microstates. Each molecule has V divided by h cubed times 2 mu over n raised to 3 by 2 cells. Available. So, n molecules are going to have V over h cubed 2 mu over n raised to 3 by 2 raised to n microstates. in equilibrium, because this for large n is roughly equal to the total number of states, and that's about equal to the states available in equilibrium. So this is nothing but the number of cells available to each molecule, and therefore to n molecules this is the number of cells which are going to be available. There is a catch, however. And what is the catch? The catch is that we are treating molecules as distinguishable. But they are not. All I am saying symbolically, if I make it in 2D, in this large number of cells, is that there is one molecule here, one here, one here, one here, maybe two here, three here, and so on. So any permutation between them has to be counted out. And therefore, I write omega indistinguishable, equal to 1 over n factorial, I am just dividing by that permutation, times v over h cube 2 mu over n raised to 3 by 2 raised to n. That is the number of microstates. And therefore, once I have written this, omega equal to 1 over n e n factorial v 2 mu raised to 3 by 2 divided by h cube n raised to 3 by 2 raised to n. I can now for large n make Stirling's approximation. And write n factorial as n over e raised to n, which gives me omega equals e v 2 m u raised to 3 by 2 divided by h cubed n raised to 5 by 2 raised to n. And entropy S, therefore, which is Kb log of omega, comes out to be n Kb log of, I can write this as V over n times u over n raised to 3 by 2 times some constants, which is then equal to n Kb log of V over n plus 3 by 2 log of u over n plus some constants. And this is precisely the entropy of an ideal gas. Obtained in previous lectures. So what we have done in this is calculated the entropy of an ideal gas by dividing the container into many small cells of small volume, and also the momentum space into small volume, so that the volume of the cell in phase space is h cubed, and then counted the number of states, took care of the indistinguishability of the particles, and calculated the entropy. What you should try is, if I did not have that indistinguishability of particle taken into account, what answer would I get and how it would be wrong. So, with this I conclude this short lecture. Entropy of an ideal gas has been calculated by counting the number of microstates available to it, and we obtained the same expression as earlier. And as a homework, I am leaving it for you. Find out what would happen if n factorial was not taken into account. Thank you.